Good afternoon, CS109. How are you guys doing today? Woo! Yay, fantastic. We have an exciting class. We get to talk about some of the probability behind ethics and machine learning. And boy, is this an important topic. We've learned some pretty interesting machine learning in CS109. And we are currently living the experience of watching the world contend with smarter and smarter algorithms, and it brings up two important things. I'm glad you guys know machine learning because maybe you'll do something really helpful for the world with it. And also, it just feels like for us to understand what's going on in this world, we should know the machine learning that is impacting our society, and we should be able to see it, look at it with a sophisticated lens if possible. And that's what we're going to do today. Okay. Oh, and this is like such a cute thing to start out with. I've been thinking about like what is my own personal basis of ethics, and before we jump into this lecture, I just want to tell you where I think I am right now. Where does this idea of human goodness come from? It's a really interesting ethical question. Before we jump into like our cool lecture, I want to tell you that I'm kind of gravitating towards this Mensch's philosophy of ethics. And the Mensch's philosophy of ethics says that there is goodness in all of us. There is a sprout of goodness. Goodness is not something that is given to us. It's not something that comes later in life. It is in our hearts from the beginning. And some people feed those sprouts. So he uses this agricultural metaphor of the goodness is a sprout within us, and if you water that sprout, it will grow and germinate into the fully benevolent person that we are all capable of being. And he often argues at this point by using the allegory of the baby and the well. If any of us saw a baby walking towards a well, and if we thought that baby was going to fall into the well, you would have this not reflexive, conscious, but very predictable reaction to go help that baby. And in fact, all of us can just feel uncomfortable imagining a baby falling into a well. And he says this is his example of saying there is something hardwired about humans that has some goodness. There is that sprout in us. Some people don't exhibit a mature version of that sprout, but it's everywhere. And I just love this because you guys kind of know me by now. I'm kind of an optimistic person. I do see this goodness in everybody, so I do like this ethical construct. But my own personal ethical construct is a little bit less important than what we're going to talk about today. The framing for today is very simple. AI is impacting our lives all over the place. It lives in our smartphones, there's security cameras, social media, all these different facets of our life. We're starting to see algorithms play a role in human existence. And therefore, we must think about AI and how it could be fair. There's a few ways of thinking about this. One is with great power comes great responsibility. Another way of thinking about this, there's a whole field and set of careers in people who are thoughtful about what fairness means in this new phase. So, I said at the beginning of class, no matter what your interests are, there is something you can combine with probability. If you're into dance, you can do dance and probability. And certainly if you're into philosophy, there's a lot of room for careers in philosophy and probability. Now, we do live in a time with real work to be done, and sometimes the affordances of machine learning can be helpful. We can all imagine better healthcare. I think of my daughter who has cochlear implants, and like the AI in those cochlear implants will make her life better. We can make smart grids to be more intelligent about how we can balance electricity in this coming electrical age. And maybe we can increase access to high quality education. There's all this real work that could be done with machine learning. But also, it is worth talking about some of the examples of shortcomings where we can look at deployments of machine learning and think, that's not good. And some versions that show biases. Sometimes, computer science can hit beyond biases. And in fact, we'll talk about this example later. And there's just case studies we can point to where like there could have been a better way. And we're going to see if we can come up with a nice construct for that. Can I give you guys learning goals? Couple things. Let's imagine, where would we like to be when we walk out of today's class? I would like you to understand the limits of this idea of fairness through unawareness. That's something I would like everybody to know. I'd like you guys to know these two ways of measuring fairness, and there's sub way of relaxed calibration. I want all of you guys to know that. In fact, those are things this is something you will need for your problem set. Now, this isn't something that I'll test you on, but I also want you guys to walk out with some sense of techniques and principles to mitigate fairness issues. So that's our goal for today. Does that sound good? Okay, let's do it. there is this other medical, which is like how to become a responsible scientist and not show up in the news, like this researcher. Okay, a couple concepts that are going to come up in today's class. What is a protected demographic? What's the difference between distributive harm versus quality of service harm? And then what is fairness? What's the philosophy of procedural versus distributive fairness? And then these different definitions of fairness. So you're going to see a whole bunch of very technical, interesting things that come from the world of philosophy that apply to the world of computer science. And then I did want to put up this warning. This is my own take. By the way, this is a lecture made by Katie Creel and myself. A lot of the research done on fairness comes from the US, especially fairness in machine learning. And I do think of that as a kind of funny meta bias. Like we'll talk about fairness, but we mostly centered within our own community. And you can imagine every community has axes of discrimination that are worth talking about. So even though our examples do come from the US, and I would like to highlight that, the framing of what you will learn does go beyond the sorts of axes that you will see in the US. Okay, a little bit of review, shall we? Machine learning, we've been learning about it for a while. And particularly, we've been talking about black box models, where you have a model which we can take in some inputs and make a prediction, and that model is governed by parameters. We call it black box model because we imagine using it like a black box where you just put your inputs in it and outputs come out. And particularly we've been talking about classification algorithms, where your inputs could be some set of features for an individual, and the output could be some sort of discrete prediction, like a 0 or a 1 for a class label. We've talked about two major algorithms. We learned about naive Bayes, and then we learned about logistic regression. I do want to tell you something that we didn't go too deep into, but is very, very interesting. If you took logistic regression, some people notice that if the input to the sigmoid is positive, it predicts a 1. And if the input to the sigmoid is a negative, it predicts a 0. And so you can think about this set of points. Like, what are all the inputs where the input to the sigmoid is a 0? So it's perfectly between the positive and negative. And for those of you guys who have seen this before, you might recognize that this is the description of a straight line. So what this is telling us is that logistic regression, imagine you only had two features, because then I can visualize it. You only had features x1 and x2, and based on that, you're either going to predict a 1 or a 0. The idea is that logistic regression is only able to draw a straight line between the 0s and 1s. And if it can find a nice straight line, it can do a perfect job on this task. But if your points aren't linearly separable, it can't do a perfect job. Does that make sense? Very cool way of understanding the limitation of logistic regression. It does pretty well, but we can think about the cases where it will break. Of course, if you have more than two features, it's really hard to think about this because you end up having like a straight line in higher dimensional space, but it still has this straight line sort of property. Interestingly, turns out naive Bayes is also creating a linear separator, in that there's no interaction between the different features that are allowed in terms of making its prediction. So both logistic regression and naive Bayes have this similar limitation. And then in Wednesday's class, we took it to the next level. We're like, well, what if we wanted to have more powerful predictors? And we did. We said, hey, logistic regression, you kind of look like a cartoon model of a neuron. What if we just stacked logistic regressions on top of logistic regressions? Would that be crazy? And at first the world thought yes, but then the world got powerful computers and said, not crazy, game changing, and that is the backbone of all modern AI. A bunch of logistic regressions put together called neural networks. It turns out these neural networks can make predictions that are much more sophisticated than just straight lines. We saw them in class. We talked about how they make their predictions. We even talked about how they use chain rule in order to gain intelligence. So you can use maximum likelihood estimation, not on just one logistic regression, but on a whole neural network of many logistic regressions. What a time to be alive. And this was an interesting thing that we pointed out in last Wednesday's class. Not only can they learn something more complicated than a straight line classifier, when they train neural networks on things like recognizing faces, the craziest thing happens where the first layers start to become edge detectors, the middle layers start to become part detectors, and final layers start to look like ghost faces. And the crazy thing about that is even though these were just getting their weights from MLE applied with chain rule, they learned something that is so similar to how our human brains work. If you looked at our human brains, the V1 cortex is an edge detector. And if you looked at what particular neurons are looking for, it looks a lot like that. Later in our brain, you find part detectors. And if you looked at what sort of inputs would most stimulate different neurons later on in your V2 cortex, you would see stuff like that. And later on, again, you get these ghost faces. Insane. Something crazy is going on. But it turns out these neural networks, while amazing, are not panaceas, and not every example of neural networks applied to human problems has been successful. We're going to talk about places where this stuff is broken. And in order to do that, it is worth noting that not every broken neural network is equally bad. And so let's bring in our first idea from philosophy. Thank you. There are different ways of saying, whoa, that model was really janky. Here's one. We think it is bad if a neural network that does something wrong introduces a quality of service harm. And a quality of service harm is one where we say this neural network works better from certain demographics than others. So for example, maybe you have generative art or facial recognition and it doesn't work for everybody equally. That's considered to be bad and harmful, but not nearly as harmful as if you had machine learning that does something called a distributive harm. We think that there's particular opportunities, resources, or information that are really essential. Like, for example, getting a job or getting a loan or getting into a school. These are really important decisions. So if neural networks start to make mistakes over here, we think of that as even more harmful. And then finally, just to cap off this conversation, there are existential harms. I'm not sure when we're ready to talk about this, but do we need to start thinking about when AI becomes intelligent? I'm not sure. I feel like I would just be speculating as much as anyone else. But we do think of degrees of harm all the way from quality of service harm to existential harm. Let me give you two case studies that give us an idea of AI producing quality of service harms and distributive harms. You guys ready? So my first case study for you is a case study in quality of service harm. And it comes down to these cameras that were actually released and were trying to do autofocus. But the autofocus did not work if you were not white, and particularly would make some awful decisions for different demographics. How did this happen? We consider this to be a quality of service harm. One way of telling the story is to go a little bit back into the world of understanding neural networks. So I told you the story on Wednesday of a neural network that was trained to look at images and tell you what's in those images. The neural network, we got really good at predicting, whether or not an image was one of 1,000 or more than 1,000 or 22,000 categories. But can I show you some places where that neural network makes mistakes? And these are a little bit more neutral than what we just saw. These really, really smart neural networks that can perform almost as well as humans make some pretty hilarious mistakes. So for example, it's pretty sure this is a sea lion, and it's pretty sure that this is a manhole cover. What could possibly lead to this very intelligent neural network making those sorts of mistakes?
Problems with the training data.
Oh yeah, totally. But can you tell me a little bit more than just problems? Because you're right, but it is worth getting a little bit more deeper into that. What do you think? What sort of problems? Why the manhole cover for that particular image?
Lack of coverage for that specific feature. And because it has so few data points to choose from, it can pick and choose and get noise.
Yeah, so it's probably not seen enough dragonflies. That's certainly the case. But there's something specific about this picture. Yes?
I think it's the angle that it's taken at, and even for the sea lion photo, most sea lions are seen doing that thing.
Yes. Okay, so angles definitely is part of it. An idea?
Not to just read off the slide, but I mean, it seems like texture comes into it. The sea lion has a smooth surface, and the manhole cover is sort of graded as well.
Yeah, it turns out they get really obsessed over things that humans can see past. For example, they're really into textures. So this just happened to have a texture that looks like a manhole cover, and this happened to have a texture from the water over here that looked like a sea lion. Now, there is a good argument that it's just a data problem. So training data can really be a source of biases within neural networks. So what you train your neural network on really does matter. There's lots of ways of telling the story. One story is what we just saw. You know, it got confused because it saw too many textures associated with manholes, and so when it saw a particular texture, it always associated with manholes. Here's another way, though, of getting a little bit deeper into this data problem. Imagine you have a classifier, and it could be linear, it could be more complicated, but let's imagine linear for now. Imagine you now have a population that has a majority group and a minority group. In the majority group, here's how you would classify class 0 from class 1. But for the minority group, let's say it works pretty differently. When you put all this data together into your data set, imagine you're learning a linear classifier. Is it going to be paying attention to the signal that comes from the majority group or the minority group when it's trying to figure out some classifier to best split the circles from the pluses? Talk about it with the person next to you for a minute, and then we will talk about what will actually happen together. Okay, go for it. I'll take a chance to draw over here. Okay. I'm sure a lot of you guys came to something like this. It's using maximum likelihood estimation to train. And so the likelihood is going to treat each point equally. Every point will have exactly one vote. And so because of that, because there's so many more points voting for an algorithm that separates like this than there are coming from the minority demographic, MLE really wants to just ignore that minority demographic and just focus on what is the overall trend. And that really comes from the fact that MLE has, whether or not you're in the log version, it has that sum over data points, or if you're in the non-log version, you have the product over data points, where it treats every single data point the same. Okay, so at this point, lack of data can be a huge problem. And in fact, going back to that camera, we really do think that is one of the biggest problems, was just one group looked like a minority to the algorithm, and then the algorithm just hadn't been trained on enough data and was making bad mistakes. It was trained on a faces in the wild data set, which was maybe unsurprisingly 84% white and 78% male. And because of this, it did poorly when it was out of distribution. And actually, this is something that we've gotten much better at. They started this process of pointing out those mistakes. They took a whole bunch of models that were in the wild that had been published and were actually being used and showed how they were making bad decisions based on demographics. And then they produced data sets that you can use that are much more balanced across different contexts that people might be coming from. And once people started training on these data sets, those particular examples that we saw became less prevalent. So anyways, cool little story that took place here at Stanford. Now, there are other levels of harm. So that was an example of quality of service harm, but things get a little bit more serious when they affect people's lives. And that makes sense. Like if you're making a decision about whether or not somebody goes to school or prison, that's a different level of harm if you get it wrong. And here's a case study of a distributive harm in AI. So there was this case of St. George Hospital. It's a medical school, and they had a whole bunch of applicants. They'd have 2,500 applicants. They would interview approximately 625. So 3/4 of people get rejected between this stage, and then eventually they offer spots to 425. So 70% of interviewees are accepted. In 1979, one of the deans had this great idea. They said, hey, we've got a lot of historical data of people who have applied and gotten past this stage. I could train a classification algorithm to decide who is going to get to the stage, and we can just have a computer do this whole first pass. So here is the timeline of what happened. 1982, he argues that he's built this classifier, and then he argues he's getting 90 to 95% classification accuracy. So when he makes a prediction, 95% of the time, it agrees with what a human would have said on the panel. That sounded like high enough accuracy, so in 1982, they started using it. Then later on, there was an internal review which asked, why are applicants being weighted by factors like name and place of birth? When they actually looked into the algorithm, it would be putting weights on things that people thought weren't that important, and it led to a review of this algorithm. And then eventually this went to ethics hearing because it found out that the name and place of birth were being used to dock points from female and non-Caucasian applicants. So I guess this story tells us of, hey, when you make mistakes, it is much worse when it's affecting something like, well, people end up in school. Now, that was just to give you a case study of these two different harms, but along the way, we have picked up some insights. We have this term in AI, garbage in, garbage out, which means if you have bad data coming in, you will make bad predictions. If we go back to the St. George's one of the reasons that the algorithm was making biased predictions is because before the 1980s, the humans were also making biased predictions, and the algorithm learned to recreate the garbage that it was trained upon. Similarly, we can say, improper use of sensitive features, that algorithm really shouldn't have been looking at things like people's names. That's a red flag that says that should not matter for whether or not you're ready for medical school. And then there's this idea that it's very believable that somebody who trained this algorithm didn't intend to be evil. Like they maybe thought they were doing something pretty reasonable, but just having not thought it through, they ended up creating quite a lot of harm. So at this point, we've just pointed out a couple types of harm. Can we get a little bit more formal about fairness? And the answer is philosophers are so excited to tell us, yes, yes we can. We've been thinking about fairness for a long time. We can actually get into more specifics about how we can call an algorithm fair or not fair. To start this conversation, it's worth pointing out that there's two big fields of thought for what we call fairness. One field of thought says fairness should come from the procedure you use. They call this procedural fairness. So what is the process of your classification? And what do you do to ensure that your algorithm doesn't rely on unfair features? That's procedural fairness. And there is another school of thought that says, well, what really matters is the outcome of the decisions you make. And so there's these two big philosophical camps. Let's be fair in our procedure, or let's be fair in our outcome. Let's jump into a few different definitions of fairness that speak to these different philosophies. The first one speaks to procedural fairness. And a lot of people historically subscribe to this being a good idea. The motivating idea for this first definition of fairness, fairness through unawareness, is the best way to stop discrimination is to stop discriminating based on race. Wait, so that's a Chief Justice Roberts. That's a little bit obscure, so let's unpack it. It's saying that if you're making a decision, if you know nothing about somebody's sensitive features, then you'll make a good decision. That's the idea of unawareness. Be unaware of the demographics and you'll be fair with respect to demographics. How to do it gets a little bit more interesting. The first idea is to exclude sensitive features. So if you're making a prediction, it is procedurally unfair if you're looking at any of these protected demographics. And the second idea is we also have to be thoughtful about proxies. Let's jump into that a little bit. It is worth also noting, what do I mean when I say protected groups? In the US, there are legally protected groups in a lot of different important, cases. The idea of a protected group often means that regardless of people's race, color, national origin, religion, age, or sex, sexual orientation, physical or mental disability, or reprisal, people should be getting fair decisions made for them. And reprisal, I think, is like, if somehow somebody had been harmed in the past, they shouldn't be discriminated in the decisions that are made against them in the future. This is the definition that comes from the Equal Employment Opportunity Act, but this same definition lives in a lot of places in legal code for the US, like, for example, housing and loans. So this seems pretty reasonable. But can we jump into how fairness through unawareness can be surprisingly difficult? Let's take some people who live across the street. Facebook. They do ads, and at some point people would be publishing ads on Facebook for housing. Housing is important because it's legally protected with respect to those protected demographics. Now, I've never made an ad in Facebook, but here's how I understand it works. When you go to make an ad, at some point you had an option of saying, give me lookalikes. And what lookalikes mean would be like, you would create your ad and you'd be like, here's 5 people. I want my ad to go to people who look like these 5 people. And they did this for all their ads. And at some point in 2018, some people said, that is not a good way to do advertisements for housing, because advertisements for housing are not supposed to be biased based off of these protected demographics. And Facebook had to change their algorithm. And so Facebook made this change. They said, we're going to do fairness through unawareness. We could do lookalikes, but our algorithms are not going to look at any of the protected demographics. We're not going to look at the age of the lookalike. We're not going to look at the gender of the lookalike. We're going to look at the relationship status. We're not going to look at the religious views, the schools, the political views, any of this. We're not going to look at any of that. You can still give lookalikes, but we will be unaware of their demographics, and therefore it will be fair. Okay, well, anyway, we'll jump into this, but it turns out, long story, is no. And I'm going to give you guys a second to try and think about why. Now, this is a funny plot. It comes from a paper which basically said, hey, Facebook, your new lookalike thing still is able to pull people based on demographics. So what they did is, can you try to flip this X and Y axis? Because the X is what the researchers were controlling. They would make lookalikes with different fractions of men. And they did this in the old version of Facebook and in the new version of Facebook that didn't look at demographics. So, in this set of lookalikes, there'd be no men at all. And in the top set of lookalikes, there'd be 100% men. And then the yellow one is when they were looking at demographics, and you would actually get 0 men, and men that looked proportional to the lookalike distribution. But when Facebook didn't look at demographics, look how closely it was able to produce the same fraction of men as in the lookalike set, even though the algorithm was not looking at any demographics at all. How is this possible? Algorithm doesn't look at whether or not somebody is a male, but it can figure out a population with the exact same proportion of men as in the lookalike population. A little bit of mystery, but a mystery that you guys could figure out if you talked with the person next to you for about a minute. Okay, so think about that. How could Facebook still be pulling out the right the lookalike percentage of men? Okay. How does this happen? They said don't look at gender. They said don't look at age.
No, I'm not looking at your age. I'm not looking at any of that.
Anyone have an idea? Yes.
I guess maybe they look at other features commonly associated with no users.
Do you want to give me one that you think maybe you could hypothesize might be associated?
Maybe like shaving products.
Oh yeah, like do you like shaving products? Yes. You know, everybody shaves. Maybe like your movie selection. I'm not saying that, you know, we don't all like the same movies, but maybe if you're like all Jurassic Parks and, you know, Star Wars, then maybe that can just influence. But if you put enough of these features together, like, you know, maybe this doesn't tell you for sure, and maybe this doesn't tell you for sure. But there's this interesting result, which is as we add more and more features, like you tell me more and more about a person, even if you don't tell me their demographics, I can predict their demographics better and better and better. Like, as you give me more of these things and more of them leak some information about demographics, you put it all together, and by the time you're Facebook and you've told me everything about this person, like their friends, their likes, you know, their history on the social network, then you have a really good way of guessing their demographics without being told. And we call those proxies. Yes?
Why would we add all that redundant data in the first place? So like what does your movie interest have to do with wanting to rent a house?
Good question. It should not. I agree with you. But the lookalikes algorithm did that because people would do ads for things that were not houses. Like maybe you want to give ads for, I don't know, you're selling like the coolest Piech app and you want lots of people to buy it. And you think somehow like people's likes are going to be really important in predicting who's going to buy your Piech app. I'm not trying to sell the Piech app. It's staying free forever just for 109. But does that make sense? It's because it was for the ads platform and they thought these things would be important for ad sellers. Facebook, their customer are the ad buyers. Yes?
Don't they have our pictures?
They have our pictures. I believe the lookalikes, yeah, might have even been using the pictures, possibly. I don't know, but if they did, that would be a really strong signal, and maybe you wouldn't need, you know, like 80 features to predict if somebody's male. Good question. I owe you a Mandarin, but come forward after class. Okay.
I have a question.
Yes.
So, go to the previous slide. So, how much features, how much information can I tell without really compromising when you're figuring out?
Ah, okay. That's a deep question. So the question was, how much information could I give you without compromising your proxy? It depends on the feature itself. And if we had a set of features, we could talk about, you know, the probability that somebody could predict this demographic. You know what I would probably do to answer that question? A simple way. I would take the features and I'd take the data I have, and then I'd build a deep learning or logistic regression model that would try and predict the demographics. And I would see how accurate it got, and that's how I would test. But it depends on the features, and if you have the right proxies, it's just not that many. Such a good question, I love it. Okay, so at this point in our story, we would like to get formal about fairness. And the first natural thing was, well, we'll be fair by just not looking at the demographics. But it turns out that's really hard. Fairness through unawareness is really difficult to do, which maybe invites us to start thinking about this other philosophy of maybe we can be fair, but by looking at outcomes. So we can try fairness. If not through unawareness, then fairness through awareness. Let's be aware of demographics and make sure that our algorithms are fair that way. Now, we've talked about this in section before, so this is a little bit of a review, but it's review worth restating because you're going to need it for your problem sets. If you have a classification algorithm, one of the things you could do is you could build this joint distribution table. This is a joint distribution between 3 random variables, which you can calculate based off your training data. So one random variable is, for any point in the training data set, you can calculate D, which is going to be your protected demographic. Now, there could be more than 2 groups, but just to keep it clear or simple, we can say we have 2 different demographics, D0 and D1. But because you have a training algorithm, there's other variables you have access to. So G, aka Y hat, could be your guess. And G is the guess of your model. So if you put this training data through the model that you're evaluating, if G is 0, it's going to guess that the label is 0. And if G is 1, your algorithm's guessing that the label is 1. And then there is a separate thing. The guess of the algorithm is not always correct. So because this is training data, you also have access to the truth, aka y. And the truth could say, in fact, the true output of this algorithm was 0, or in fact, the true output of this algorithm is 1. You could take all your training data and you could have a joint table because you could think about these random variables together. From these random variables, there are many definitions of fairness through awareness. We're going to just talk about a couple of them that are the most commonly used. The first one is, hey, maybe I'll think about your algorithm as being fair if it satisfies parity. And if you read the algorithm definition of parity, it gives a probabilistic definition. It says the probability that you guess 1 for somebody from one demographic is the same as the probability that you guess 1 for somebody of another demographic. So regardless of people's background, your algorithm has the same probability of predicting a 1. And maybe we think that this is a good sign that the algorithm is making fair decisions. But it's not the only good sign. A different good sign is that, I want condition on demographics a different thing to be true. The thing that I want to be true is that G equals T. Now that's different from saying G equals 1. This is saying that G equals T. What's the difference? Yeah.
The parity thing on the board, I believe,
differs from what's on the slide.
Am I missing one here? Better?
Mm-hmm.
Yeah. Yes.
Sorry, so is it saying that the algorithm predicts correctness regardless of demographic or regardless of whether demographic is included?
Yeah, so this is saying regardless of the true demographic of the person, the algorithm is just as likely to make the right decision.
So not like whether we include demographic or not.
Yeah.
Just no matter what.
It could be included, it could be not included, but the outcome is that correctness is not conditionally different based on demographic. You could say that it is conditionally independent of demographic. Yes, question behind you.
I was going to ask that.
Yes.
Said it's independent.
Yeah. So knowing demographic won't change your belief in whether or not the algorithm will get it right. And this first one, parity, says knowing the demographic won't change your belief that it's going to predict a 1. Those are subtly different things. Yeah.
Is there a situation where we wouldn't want it to be the same for the demographic? Like, would it in some cases actually make sense and be beneficial to actually match the true algorithm?
Yeah, there are cases where you might say, for this one particularly, you say that, for different demographics, maybe there is a different underlying rate. So an algorithm that's always predicting 1 independently of demographic, then maybe it's inaccurate because there's a different base rate. But some people say that even if there's a different base rate, that might still be something worth aiming for because we'd like our society to move towards this. But then this is a little bit more saying, there could be a different base rate. So you could be predicting G equals 1 in different rates, but you're correct the same amount of time. And they're different philosophically, and there's certainly been algorithms where I've seen people debate very hard about what they consider to be fairness. Because it does turn out that not all of these fairnesses can be satisfied together. You sometimes have to make a decision of what fairness you think you're going to be going for, and that really depends on the case. I do want to note a little bit more that there is a legal standard for what level of independence we're looking for. I know independence is binary, you're either independent or not, but people do allow these things to be slightly different in some legal situations. So for example, the US has this legal standard of disparate impact, which says an algorithm is acting in a biased way with respect to calibration. And that's not saying that these two things have to be exactly equal. It allows the ratio to be, either this ratio has to be greater than or equal to 1 minus some epsilon, sorry, that should be 0.2. And regardless of which thing goes on the numerator. And we think that if this numerator is close enough to being 1, then we think that this follows under calibration, according to legal standards. Now, there is this historical story, which is not that historical. It's not that old. Back in the day, there was this algorithm that people were using in California and Florida to predict whether or not somebody would commit a crime again. And this was very important because it was used in courts in order to decide if people would get lenient sentences or stronger sentences, and I think also to decide whether or not people would be given bail. So this algorithm, which has the name compass, was being used in these states, making predictions. But regardless of whether or not you measured calibration or parity, it was doing a bad job, and that the gap was very large between black inmates and white inmates. So, at this point, I do think fairness through awareness has a lot of strengths. Fairness through unawareness is very difficult. Fairness through awareness has this idea that, like, okay, we're going to pay attention to demographics and try and be fair. But it does have weaknesses that are also worth pointing out. The first one is you have to make a stance about what your definition of fairness is. And there's more than these two. There are like 17 definitions. There's people in CS and philosophy who come up with new definitions all the time. And so you have to choose what fairness means to you. There is this more subtle harm, though, that can come from fairness through awareness that is worth pointing out. And this was came out in a paper by Cynthia Dwork and Omar Reingold, who are professors here in the CS department, of this self-fulfilling prophecy challenge that can come through fairness through awareness. The idea is, let's say a classifier is made to be really good at one of these definitions of fairness. If it turns out that pursuing that fairness means that the algorithm is a lot worse at choosing strong candidates in different groups, then you might see a quality of service disparity later on, which might lead people to look at differences in the groups and assume that there is a stronger difference than there are between the groups, which can change people's mindsets to think that some group is stronger than the other, which they call allocation disparity. And so there is an argument for there's a lot more nuance to this, though that's something worth keeping in mind. This is still the state of the art that a lot of people go towards when we think about fairness. Okay, so where are we in CS109? Yeah, great question.
Yeah, I was just wondering, so I mean, in all of these, I understand that not considering demographic information like race, for example, would be really important, especially if you're looking at like crimes. But if you're looking at something that's not like humans discriminating against humans, but like diseases discriminating based on genetics or something like that, how do you draw a line between not including race because you don't necessarily have enough data, but still that being a major factor that contributes to different disease outcomes for people?
That's a good question. So, okay, let's think about the disease thing. Often fairness comes down to like decisions made by humans. So let's imagine in the world of disease, what's a decision that humans could be making? Yeah, okay, let's say whether to treat or not. So in this world, whether to treat or not is a decision that you're making. It's a decision that we could think through the fairness construct. Okay, so now that I'm in this world, what was the question? Sorry.
So, I mean, I guess, like, for example, a doctor is trying to use this to decide, should I treat this patient or not? And maybe it's shown that for this subclass of patients, this race of patients, this treatment doesn't work as well for whatever reason. That's what our data shows. That might actually be true. But if we're not ignoring that, then we're potentially putting those people at harm. Yeah,
so that's a good argument, I think, for you should not be using parity in that case. You should not be saying treat at the same rate for the two different groups. I think that's still an argument where you might want to say you're calibrated, which is I'm not going to treat at the same rates because we know that there might be different effects, yet I want the accuracy of my decision to be the same. So if I decide to treat and treat was the right decision, you know, that's +1 for accuracy. And if I decide to treat but that was the wrong decision, that's a 0 for accuracy. And we want that rate to be the same.
Okay, so in calibration, you're still, like if you're training an algorithm, you can still use demographic data to train it?
Yeah, potentially. I guess calibration doesn't speak about the procedure you use. It just speaks about the outcomes. Though, is it possible to try and do both of these at the same time? Absolutely. And that I feel like that's maybe a good practice. Like, don't try and use demographics in your prediction, and then make sure that your outcomes are somehow fair.
Even if demographics have been shown to impact?
Ah, okay. No, maybe that is a case where you say like using demographics could be important. So maybe, yeah, maybe in the particular case you brought up, that might be a good example for we want fairness through awareness, and we particularly want calibration and not parity. Yes?
If a big model is going to infer demographics through proxies, why not just include it at the beginning of the model if we're so sure based on these like common considerations that it will be reconstructed?
So, I mean, going back to Facebook, they're legally not allowed to. So like, you're not supposed to be looking at demographics when making the decision because the law was built around procedural fairness. So even, okay, so your question is hey, these algorithms are going to build proxies. Should we just throw in demographics? And I'd say that the arms race goes in the other direction. We shouldn't include the demographics, and we should be mindful about proxies, and we should think of ways that we can deal with the proxies. Because it turns out there are things we could do. Want to learn more about those? Okay, let's jump into it. Okay, so at this point in class, we've said, hey, machine learning is an interesting tool, but it's possible to create harms. We've talked about 2 specific types of harms we could talk about. Then we said, okay, we would like to be fair, and so that whatever harm, if we're going to possibly have harms, though it'd be great if we had 0 harms, we should be fair. And we've talked about 3 versions of fairness. Fairness through unawareness, and then we've got parity and calibration. Now, at this point, though, I think it's nice to leave our story on the note of what could we possibly do about it? So here are some pro tips. So one of the pro tips is being balanced in your training data. That comes from our first set of stories. You know, if you're going to be training something that does facial recognition, try and represent all people in your training data. There's this other thing that's growing in the world of AI, which is being very transparent about where your black boxes come from. So if you make a black box algorithm, there's now this thing that you can attach to it called a model card. And it tells everything, like, you know, who are you making this model? What is your intended use? What are the factors that go into it? How did you evaluate your model? What was the training data that you allowed on it? And what was the quantitative analysis? Like, what are all the measures you've done maybe about parity and calibration? So this is becoming standard. And then here's a funny little story that actually starts in CS1 that's kind of interesting. One of the things you could do is you could ask, can we train the bias out? So back to your question. If you include demographics, of course, it can make decisions based on demographics. If you exclude demographics, it might make decisions based on proxies. But can we build an algorithm that tries to remove out those proxies? And that was a question that 2 seniors at Stanford, former CS109 students, were interested in. They're like, can we remove these proxies? So they looked at Compass. They actually there's a public data set now on Compass on decisions it has made. And in Compass, the inputs look like all sorts of data about an inmate. It has their zip code, their past crimes, their age, lots of inputs like that. And then the prediction is recidivism. Are they going to commit a crime again? Now, first of all, when I talk about these inputs, a whole bunch of red flags should go off. Be like, why do you care about their zip code? Why is that going to make you make a good decision? And just to remind you guys, this was actually used in the state of California and Florida. Now, Compass, from this data, we can show was very biased, whether or not you measure bias in calibration or in parity. You want these gaps to be 0 because the gaps are the difference between the size of your equations. So the bigger the gaps, the bigger problem you have, and they had pretty big gaps. So these 2 students said, okay, what if we tried to be creative and came up with a way to remove the bias that was in this Compass algorithm? And so they built a 2-step neural network. The first neural network was the prediction, and this was recreating something like Compass. You would take in the inputs, and then you would predict out whether or not somebody would recidivate. But then they had a second neural network that would take the output of the first neural network and then try and predict demographic out. And they said, if you train this so that you do really well on model 1, so likelihood's really high on model 1, but then they said, make likelihood really low on the second one. So this combined model should be really good at making its prediction, but very bad at pulling out demographics. And the theory was if you did this, then you could remove some of the proxies that exist within the data. It worked very well, so they ended up with a model that was just as accurate, but they were able to remove calibration gaps and parity gaps. But my favorite thing about this paper was they did all these cool things, and then their big claim in the paper from the beginning to the end was, yes, we can do this, but you should not be using black box algorithms to make recidivation predictions, and you should absolutely not be using these features, like zip codes shouldn't matter, and it should be something that we can be much more thoughtful. Yes, judges have been biased, but biased algorithms are not the direction that we want to go towards. And particularly, they picked at this idea of using a black box algorithm because it's something that defendants couldn't argue against. If the black box algorithm just said like, yep, you're committing a crime again. No, I'm just joking. You haven't committed any crimes. But I'm just, as an example. And you can't argue again. You're like, the neural network's wrong. You're like, prove it. You're like, oh, look at the weights. The weights are wrong. And it becomes really unfair to the person to argue against a black box algorithm. Which kind of brings us back to an idea we saw earlier in class. Neural networks are great, but people can't really argue against them. Black boxes might be very accurate at making predictions, but you can't understand or figure out how it's making its decisions. You know, there's some things we can do, some nice little tricks we can do to try and understand what the neural network is doing. But the long story short is understanding a complicated black box can be as hard as understanding how a human makes a decision. That's less true for Bayesian networks. You know, Bayesian networks is this thing we learned about earlier where you have variables and you have conditional probabilities between the variables. If somebody had an algorithm that was making prediction using a Bayesian network, it's a lot easier for somebody to say, hey, this is why your algorithm is wrong in my case, because even though I have this variable, this conditional probability is wrong for me. Okay, so that's a nice little aside. So one of the things you could do is maybe you could try and train out bias, but you should always be careful about what task you're solving. Actually, maybe I should have put that in here. How come I didn't put that in there? It's like one of the most important things. Like, choose the task you're working on. Think about what the world really needs, and can you make something that will make the world a better place? Like, for example, like you think about the person who made the gaydar detector based on people's photos. Is that actually what the world needs? But you imagine, like, what if instead of doing all that intellectual work, we put that intellectual work into making better smart grids so that we can better balance power? Like, maybe that's the most important thing. But anyways, here's a fun little story, though. One of the interesting things is you will go on from here, and some of you guys will go work in tech companies, and it's interesting to think about what responsibilities we can have, and even if you're in academia or tech companies, what responsibility can we have if we're in those roles? Here's a nice little case study that's quite interesting. This is from a while ago. It's in Polaroid. So back in the day, do you guys know Polaroid cameras? Like from the shake it, shake it, shake it? No? Anyways, okay. And so you take a photo, it would print it, you take the photo. Actually, it doesn't matter if you shake it. Over time, it develops, and you get to see it in like 10 seconds later. Anyways, Polaroid was a popular American company. Originally, they only had one flash. And the idea was that it didn't really work with the single flash that they had on people who are not white. So it was really built to work for people who are white. But then Polaroid, turns out, was also selling it to the South African government. And they made a feature for the South African government to make the flash work so that it could capture black skin tones better. And it was used by the apartheid government to build these passbooks that were like an essential part of discrimination in apartheid South Africa. And the interesting story about this is this would have kept on going except for an engineer who worked at Polaroid who brought this to light and said, hey, this is wrong, we should talk about this. And that's how change happened. It came from inside the company. Okay, we're going to talk about a little bit more, but I thought this would be a great time for a good pedagogical pause. So we've talked about fairness, we've talked about harms, we've talked about what you can do about it, and then I'll just tell you a little about my thoughts on ethics on my own. Okay, so take 2 minutes and we'll come back and we'll continue our conversation. Thank you guys so much for following along so far. Okay, let's bring it on back for the home stretch of this lecture. Okay, post-pedagogical pause. Let's go back to learning goals. So learning goals, the first thing we talked about in terms of formal definitions of fairness was fairness through unawareness. And I hope you guys understand why fairness through unawareness is a little more complicated. That Facebook example really drove that home, because there could be lots of proxies. If you wanted to make a decision, just not including demographics is often not enough. The second learning goal, know the two ways that we talk about in CS109 of measuring fairness. So, hopefully this is making a little bit more sense. And as, even with this asterisk version of the relaxed calibration. And then we just recently talked about some techniques that we have for mitigating fairness issues. Now, when I was thinking about this lecture, I came to this decision that I don't think a lot of computer scientists want to be evil. I just don't. I've seen a lot of people. I feel like a lot of people have. Maybe it's this Mencius in me. I believe there's the sprout of goodness in everybody. Though I do think about the blind spots more and more. And let me tell you a story that you might have heard of. And you can let me know if you haven't heard of it. If you haven't, then certainly I think a story we should all know. My idea is that even though we've got this sprout of goodness in us, well-intentioned people can still break things at scale, especially while moving fast. And the story that really struck me, and actually when this developed, I think it was kind of a phase change for me as a computer scientist. I was like, oh, we must be so much more thoughtful. Like, I don't think anyone meant to do harm here, but real harm was done. Let's take a pause and think about what we're doing. And there's the story of Free Basic. Just quickly, who here knows the story of the harm from Free Basic? A couple of, okay, this is going to be a good story to hear. So the story starts with this product that Facebook wanted to give. It was called Free Basics. And the idea was we're going to give free internet to people around the world. And that's a good start. Be like, yeah, getting people access to internet feels like a good thing. Now, maybe because Facebook wanted to get something out of it, or maybe for other reasons, they made the internet be delivered through Facebook. Like, we'll give you free internet, but it comes through Facebook. So like Facebook is really the internet that you get. This was deployed in a few countries. Deployed in Sri Lanka. It was deployed, I think in Kenya. No, actually not in Kenya. But it was deployed in Myanmar. And when it was deployed in Myanmar, you had a country where a lot of people didn't have access to internet. And all of a sudden, almost everyone had access to internet. But it was internet mediated through Facebook. So like everybody had a smartphone now that could open up Facebook and you can get access to it. Myanmar had a military junta, and the military junta started a misinformation campaign against a particular Muslim minority in the country called the Rohingya. A lot of misinformation. Now we know a lot about misinformation, but at that time it was a little bit more novel. But you can imagine all these people who didn't have much access to the internet before now have it, and now are faced with a very sophisticated misinformation campaign. But to add fuel to the fire, Facebook only had 2 moderators for the entire country of Myanmar who could speak Burmese. So they had just unleashed Free Basics. Lots of people were using it. A huge misinformation campaign starts, and there's just not enough people paying attention to realize it. It led to a genocide. We'll talk about causality in a second. But the genocide that ensued afterwards was really awful. Millions of people displaced. And the UN, whenever there's a genocide, they have a mission to try and figure out what happened. And the UN concludes that this Facebook Free Basics was a critical component in leading up to this genocide. And so I think they say, the role of social media is significant. Facebook has been a useful instrument for those seeking to spread hate in a context where, for most users, Facebook is the internet. Although improved in recent months, the response of Facebook has been slow and ineffective. And, I think this is when this happened, it was such a drastic harm. Like, we'd thought about, I'd seen examples of small harms, medium harms, and then all of a sudden this was like, that's a big harm. And I don't think anyone at Facebook was like, yes, genocide, we're gonna do it, right? And that's not what people were thinking. I think it was just a blind spot, right? They're like, we're gonna give internet, it's gonna be great, it's gonna go through Facebook, that'll be fantastic. Why moderate that much? And they just didn't see this big misinformation problem and what it could possibly lead to. And so, you can imagine this move fast and break things mentality, though it seemed really exciting at the beginning, really came into conflict with reality when they started to see these big blind spots. And I think that's also especially true at scale. Facebook was still just used in universities probably wouldn't be facing consequences like genocide. And suddenly at scale, when you have blind spots, it can certainly be worse. Facebook has been asked, what's the answer to this by lots of people. You know, we've seen misinformation, not just in Myanmar. And their answer, interestingly, is that the only way we can prevent hate is better machine learning. And I'm not, you know, we can all have opinions on that, but it's quite interesting to think that, you know, scaled computers can be the problem, and then the claim could be that scaled computers could be the solution. Though I think some intelligent people could argue that maybe this is just a way to get around not actually addressing the issue. But the point of this wasn't really just to dump on Facebook. Yeah, I do think, though, if I could drive home a point, is that I don't think anyone that I've met in the field of computer science really wants to do harm. But we should be thoughtful about our blind spots. You know, maybe it's whether or not we're predicting somebody gets admitted to a school, or whether or not we're trying to give internet to other people. We should be humble in that if we're building something that will affect a lot of people's lives, we should think about what are all the things, the unknown unknowns that we might be facing. And then I do want, this is like a little bit of a personal thing, but I would like to highlight one blind spot that I'm trying to contend with, like I think many of us are trying to contend with. This is a computer science blind spot that worth bringing up. You guys know this story. Hopefully you know this story because it's becoming a little bit more popular. Bitcoin's using a lot of energy. And you know, if you think about it in terms of hashes per second, it's a lot. If you think in terms of carbon dioxide in the environment, it's a lot too. And despite the fact that we're seeing more evidence that this is a problem, it's really hard for us to look at this blind spot straight on. And you know, one piece of evidence I'd point towards that is that we teach a lot of blockchain, but you know, I don't think Bitcoin and the effect on the environment is something that even shows up in an ethics class on Stanford. And I will update this slide once somebody tells me that has changed. And it's not too hard to see why increased CO2 could be a problem. This is like CO2 in the atmosphere, and you can see it's become quite large since humans have started contributing. It's not too hard to know the physics of why CO2 will make our world warmer. You know, we know the fact that it can have a cool video if you're curious. It's not too hard to know that the impacts would be really harsh if we have a large change in temperature. You know, we've seen the world, or we have ways of understanding what the world was like when it was quite a lot colder and there was a lot less, or the change in temperature was a lot smaller. You can imagine when we get to the point where the change in temperature is quite deviant from what it was in the historical average, that it could be something really scary. And one of the reasons it's not too hard to imagine is that we're already starting to see impacts, like in California, fires and droughts, but other places, you know, like Hurricane Idai impacted over 3 million people. They weren't very used to getting huge hurricanes in Mozambique. One of the reasons I think that this is such a blind spot is I think a lot of people in the world are not versed in the language that you're now versed in. I think the challenge of climate change is filled with uncertainties. You know, you have to think about future amounts of CO2. You have to think about what this will do to the environment, the climate sensitivity. And then on top of that, you have to think about how that will impact people. And these could be future people in places far away. And even though there's a lot of uncertainties, one of the takeaways from CS109 is that's not the end of the story. You can reason under uncertainty. You can make good decisions based on uncertain probabilistic distributions that you might have access to. But I am also going to acknowledge that maybe this is less of a blind spot. And do you guys ever feel like it's just hard to do something about it? Like, yeah, I can tell you climate change is a problem, but then like, what are we going to do about it? And you felt like that? Yeah.
There's something that they're doing for Bitcoin specifically, or on ETH when they like swap to proof of stake.
Yes, so that's very interesting. So the point is that they have actually started to address this. Like for Ethereum, they switched to proof of stake from proof of work, but Bitcoin has not.
Bitcoin has not.
And actually, there's something really interesting to that. I was thinking, why can't Bitcoin switch to proof of stake? So there's this idea of something that's a little less democratic, but will not have this huge environmental consequence. You could do this for any blockchain-based coin. And Bitcoin doesn't change. Why doesn't Bitcoin change? It's completely decentralized. It's like, you know, there's no one in control of Bitcoin. There's no one. I feel like if any one person was in control of Bitcoin, you'd be like, yo, look at all this CO2. And they're like, yeah, that sucks. Let's change that immediately. But the great idea of decentralization seems to have hit this problem of like, there's an obvious thing that we should fix. but decentralized, we can't make that change. Anyways, this is something that I reflect on a lot as I get deeper into thinking about decentralized education. But that's a different story. You know, there is this philosophy that I sometimes find myself in, which is like, with regards to climate change, like, can't we just wait and see what happens? And man, I'm in such an uncomfortable place because I've convinced myself that I can't say that. I've benefited too much. I've produced more CO2 than the average person in the world. It's really unfair for me to say like, oh, I benefited from all this and then I'm just going to wait and see what happens, especially because I'm not a wealthy person, I'm a professor, but with the meager amounts of wealth I've accumulated, which is more than most people in the world, I probably won't be affected by the results as much. So I've benefited from burning CO2, and I probably won't be affected by the worst changes in climate change because I could move if I needed to. You know, California might not be hit as hard as places that maybe didn't burn as much CO2. So isn't it totally unfair of Chris to say, I'm just going to wait and see what happens? And there's ways of telling this story, you know, like you can imagine, this is a very extreme example, but you know, there's a lot of people after World War II who asked the question, you know, what was the problem with bureaucrats in Hitler's empire? And there's a lot of people who are like, you know what, I'm just going to wait and see what happens. That was a common idea of like, let's just see how this thing develops. So instead of ending on that note, I'm trying to think for myself, what can I do? And maybe this is interesting for you guys thinking about what can we do. I've decided on an individual level, it's really unfair because I could cut all my CO2 emissions and that just won't change things. There's big companies, there's big nation states that are producing so much CO2 that my change on an individual level is hard. And then, boy, do I wish I could affect the nation state scale. Actually, I don't really want to. But it would be cool if I could be like, hey, just this one thing, why don't we just like figure out this whole CO2? Let's make a lot of clean energy, it'll be fantastic. If I could, I would, but you know, I don't live in that world. But I do think for a lot of us, there is a sweet spot in the middle of community. And so that brings me back to the Bitcoin thing. You know, like maybe this, as computer scientists who are at Stanford and therefore have a lot of clout, you know, maybe we can start thinking about ways to talk about this blind spot that might exist around the proof of work that is behind the blockchain in Bitcoin. And then this is a very small thing. As computer scientists, if we had a perfectly clean grid, every time you run an algorithm, you don't have to worry about it. You can go to sleep happy and be like, it's going to be doing a bunch of hashes, but I know that hash is powered by the wind. And so I think all of us could sleep a lot better if we could get a clean grid in California and in our other locales. And then certainly, I don't like to think about AI as a panacea. I think we should address our problems that are rooted in things that are outside of AI, sometimes with human institutions. And yet there's probably really cool problems to work on in the world of AI. Like I've seen people who are going to predict, you know, the electrical spikes that happen when people plug in electrical vehicles. And if you figure this problem out, then you can really reduce the impact. You could predict buildings that are using a lot more CO2 and they're probably not heated well, so you could retrofit them. So there's a lot of cool things that we could do. And if any of you guys do that, you rock and you should tell me about it. Okay. Now, to end this lecture, can I just give you guys a small thing to do? Because ethics is a complicated thing. I can come and give you formal definitions, I can give you some case studies, but I really think that the work belongs in our hearts. So I'm not going to give you any more homework than I already have, but if I could give you something to do after this lecture, it'd be to give yourself some space. Maybe I should just put a period here. Man, you guys work hard. I really respect how hard you guys work at Stanford. You know, like you're trying to do all your classes, you're trying to maintain all your friendships and be there for each other. And actually just giving oneself space in general is great. Like put away our phones and like connect with yourself is always a good thing. And maybe give yourself some space and then reflect on what's your own sense of what is right. Because one of the things I've learned by working with wonderful students like yourselves is, you know, you guys have it in you. And what I really believe in your sense of what is right, and if you're thoughtful about it, not only will you guys do wonderful things, I think you'll do wonderful and fair things. And you know, both what is right and also how can you craft a life well lived with respect to what you think is right. Okay, I appreciate you guys so much. Thank you so much. Come back next week. We have just 2 more lectures and then we're done. Oh, final time. Cheers, CS109.